Hi guys, today we're going to learn about parametric equations and vectors in calculus. So basically what we're going to learn today is how to take derivatives of parametric equations, and we're going to find the arc length of a parametric equation. Okay, so we have that if a smooth curve C is given by the equations x equals f of t and y equals g of t, then the slope of C, the curve, at the point xy is going to be given by dy dx is equal to dy dt over dx dt, where dx dt is different than 0. Okay, and the second derivative is given by this. Okay, you have that the second derivative is going to be the derivative with respect to t of dy dt, which is going to be the result that you have from here, divided by dx dt. Okay, so first you are going to tell me where this thing comes from. Okay, so this thing comes from if you have your parametric equations defined as f of t and g of t. What you have here, let me show you. Okay, so what you have, what we're going to about to do to find this function is we're going to use the chain rule. Okay, so the main thing is we're going to assume that the parameter can be eliminated like you were doing this in pre-calculus. Okay, so we're going to let's go y be equal to p of x. Okay, so that's going to be the explicit function. Okay, the one that we love and we are used to take the derivatives of. Okay, and then what you're going to do here is you are going to redefine this with the functions that we have here. So what you have here is that y is equal to g of t, and p is going to be equal to, instead of x, you're going to put f of t. Are we okay with that? So this is what you have. You know this from the definition that we have over here. Now, what are we going to do here? As usual, when in doubt, what are you going to do? Take the derivative. Take the derivative of both sides here. Okay, so if you take the derivative of the g prime, okay, you have that that's going to be the derivative of the side. On the other side, you have that the derivative, you have a chain rule. Okay, why? Because you have the annihilation of f of t here inside p. Okay, so you have a p prime f of t times the derivative of the inside, which is f prime of t. Are we okay with that? After that, what you're going to do, okay, this comes from the chain rule, in case that we're wondering. What you're going to do is you're going to solve, okay, for p prime of f of t. Okay, that's what we're going to do. So how can we solve for this guy? This is the one that I want to solve for. Okay, you're going to pass dividing this guy to the other side. So what you have is g prime of t divided by f prime of t is going to be equal to p prime of f of t. And then ask yourself, what do we have here? Okay, so what you have here is that g prime of t, okay, with this. You have that is going to be y prime, okay? You know that y prime is the same as dy dt, okay? The Leibniz, notation of the derivative. And what is x prime of t? It's going to be dx dt. And what is going to be p prime of f of t? Well, this one, technically speaking, is p prime of what? X. Okay? P prime of x, you know that this one is going to be equal to, surprise, surprise, you have that it's going to be dy dx. And that's how you have the first derivative of a parametric equation. That's where the formula comes from. I hope that it makes sense. Okay? If it doesn't make sense, well, you can just memorize it, which I highly recommend you to understand where it comes from, but if not, you can always remember this. Please remember something. The dx dt, okay, which is going to be an expression or maybe a number, needs to be different than 0, okay? If it's equal to 0, you know that this is going to be undefined, meaning it's not differentiable there, okay? The second derivative is given by the situation. As well, you need to have the condition that dx dt needs to be different than 0, otherwise it's not going to be differentiable twice there. Okay, so let's apply this formula so you can see that it's pretty simple. Okay, so this one is an example with no calculator. Given the parametric equations x is equal to t squared plus 9 and y equals to 4t power 5 minus 6t power 3 plus 3, they are asking you to find the first derivative. Okay, and this is going to be the second derivative. Okay, so you already know from implicit differentiation that when you see this, that means the second derivative. Okay, so first derivative, second derivative, Leibniz notation. please get used get used to this. Okay, be comfortable using this because you are going to use it in multivariable calculus, this notation a lot. Okay, so what are we going to do here? Well, you know that dy dx, okay, is going to be equal to dy dt over dx dt. Okay, so what I'm going to find here is dy dt. Okay, so what's dy dt? Dy dt is going to be the derivative of all this thing. Okay, so what do you have that it's this one? This one is going to be 20 t power 4. Okay, then you have that it's going to be negative, okay, 18 t power 2, and then this one 0. Do you agree with that? Then you are like, I need the dx dt. Dx dt is going to be just 2t because you take the derivative of this guy. Okay, so we have the two pieces of the puzzle that we need. We need this guy and this guy. We have them. Okay, so what do you have here? What we have here, and let me put a big comma here, we have that dy dx is going to be equal to, stack them together, you have that 20 t power 4 minus 18 t power 2 divided by 2t. Now what you have here, okay, which is pretty nice, is you can see that all of them are even and all the terms here have t's. So I can simplify it. Okay, so what you have here is 10 t power 3 minus 9t. Okay, and that's going to be your first derivative. This guy that you have here is your first derivative. Now you're going to tell me how in the world I can find my second derivative. Well, we have all the pieces of the puzzle. So what's the business here? The second derivative, okay, that we use this notation for the second derivative, is equal to the derivative, okay, with respect to t of this guy that we have that it's 10 t power 3 minus 9t, and all of this divided by dx dt. But the great thing is, okay, ask yourself, can I find the derivative with respect to t of this expression? Absolutely. Can I find dx dt? I already have it. It's this one. Okay, so you take the derivative of this one, which is going to be 30 t squared minus 9, and this is going to be divided by the 2t that we have here. Now, you can leave it like that, or you can simplify a little bit more, right? If you want. This is not required. Like this, right? Either way, it's correct, right? One, it has only one denominator. The other one, well, it's more simplified, but it has two pieces. Okay, so this guy that you see here is the second derivative. Okay, what do you think? Isn't that cool and simple? So that is the first derivative and the second derivative. Let's do another one and see if you like it more. Okay, so another equation here, we have parametric equations. X is equal to 5 sine of t and y is equal to 3 cosine t. They ask you to write the equation of the tangent line, okay, to the curve at the point where t is equal to 2 pi over 3. Okay, so first ask yourself, what are they asking for? Well, they want a point slope, okay, a point slope equation, okay, because they want the tangent line. Okay, so what is the point that I have here? First, I'm going to deal with the point. How can I find the point? Well, you are going to plug 2 pi over 3 inside this expression and inside this expression to find your point. Okay, so what you have is that x of, what was it, 2 pi over 3 is going to be equal to 5 sine of 2 pi over 3. Okay, since you know your unit circle, or that's my hope, okay, you know that sine of 2 pi over 3 is root 3 over 2, okay, so what you have here is that this is 5 times root 3 over 2. Similarly, you have that the y, okay, y of 2 pi over 3 is going to be equal to 3 cosine of 2 pi over 3. Okay, so you have that this one is going to be what? What is going to be cosine of 2 pi over 3? You know that cosine of 2 pi over 3 is going to be negative 1/2. So you have that it's negative 3/2. Okay, so your point here, okay, you have that your point is going to be this guy. So we're halfway done here. Do you agree with that? So because what do you want? We want a point slope. Okay, so I have the point. Now, where's the slope? You know that the slope, okay, is going to be dy dx evaluated at t equals 2 pi over 3. Now, the business here is you need to be careful here. Okay, you need to take the derivative of what? The y with respect to t and the x with respect to t, okay, and evaluate those at 2 pi over 3. You are not going to evaluate first, right? First you're going to take the derivative and then plug it in, remember, okay? So what is the derivative of 5 sine of t? You know that 5 sine of t, which is going to be the denominator, is going to be what? 5 cosine t. And what's the derivative of 3 cosine t? Negative 3 sine of t, okay? So you have this equation that we're going to evaluate at 2 pi over 3, okay? Yes? Okay, you might tell me, well, I prefer to use tangent. Go for it. Use tangent. If that's your preference, go for it, okay? And we're going to evaluate at 2 pi over 3, okay? So what is tangent of 2 pi over 3, okay? It's going to be negative root 3, okay? So negative root 3 times negative 3 over 5 is going to be positive 3 root 3 over 5, and that's going to be your slope, okay? So I have all the pieces of the puzzle. I'm very happy, right? I'm a happy person because I have all the pieces of the puzzle. So thus, okay, the tangent line, okay, at, what was it, 2 pi over 3, is going to be the following, okay? So you know that it's going to be y minus y naught, okay, minus this one, so it's plus, okay, it's going to be equal to that, is going to be your slope times x minus that value, okay, which we have that it's going to be this one, and that's it. Isn't that nice? So this is a typical question, okay? You know that you're going to find it everywhere, okay? Finding the slope of the tangent line is the deep meaning of the derivative, so you are going to find it a lot, okay? So let's do another example that they're asking something else. How can this formulas can appear, okay, in the wild? Okay, so this one, it tells you find all the points of horizontal and vertical tangency. Okay, let's stop there. What is being horizontal, okay, when you have an horizontal tangency? You know that you have horizontal tangency when the slope is 0, okay? So you know that this is slope 0. When you have vertical tangency, you have that when what? When the slope is, back in algebra 1, undefined, okay? Now, let's keep reading. Given the parametric equations, you have that x is equal to this quadratic and the y is equal to this other quadratic situation. And you're going to be like, I don't know where to start. But when in doubt, what I'm always telling you, take the derivative. Take the derivative parametrically. Okay, so what are we going to do here? You have that dy dx is equal to, you know that we're going to keep using our beautiful formula dy dt over dx dt. So, since I don't have a lot of space here, I'm going to take the derivative of the y. So I have 2t minus 8 divided by, and you have that this is going to be what? 6t minus 6. Okay? Let's talk about, first let's start with horizontal tangency. Okay? Horizontal tangency. Horizontal tangency means that dy dx is equal to 0. So meaning the numerator must be equal to 0. Do you agree with that? When that happens? Well, that happens, I pass the 8 to the other side, so I have 2t is equal to 8, and I have that t is going to be equal to 4. Do you agree with that? That's not it, okay? They are asking about the points. So this is the value of the parameter, but what's your point? Well, you need to replug your value of t inside your expression. So you have that x of 4 is going to be 3 times 4 squared minus 6 times 4, okay, which you know that this is going to be 24, okay. Similarly, you have y of 4, okay, and y of 4 is going to be 4 squared minus 8 times 4 plus 9, okay, and this is going to be equal to negative 7, okay. So you know that horizontal tangency, okay, at the point, you have that this point is going to be 24, negative 7, okay. Now, let me separate so you don't confuse vertical tangency, okay. So vertical tangency, when do we have vertical tangency? Vertical tangency, we know that dy dx must be undefined. Do you agree with that? When that's undefined, you know that when the denominator is equal to 0. If the denominator is equal to 0, you know that 60 minus 6 is equal to 0. So when you solve that, you have that 6t is equal to 6, therefore t is equal to the beautiful number 1. And what are you going to do to find these beautiful points? You are going to plug your 1 inside your x. Okay, so you have this 3 times 1 squared minus 6 times 1. Okay, so this is giving you negative 3, and similarly we plug the 1 inside the y equation, right? And then you have that it's going to be 1 squared minus 8 times 1 plus 9, and that beautiful number is going to be positive 2. Okay, so you have that, you have vertical tangency at the point, this one is going to be negative 3, 2. Okay, so that's what we have. Those are the points of horizontal tangency, vertical tangency. Make sure that you understand the difference between being horizontal. Okay, it comes from algebra 1. Okay, the definition of the slope: horizontal, the slope is 0; vertical, the slope is undefined. Okay, so let's move on to the next example. So earlier this year we learned to find the arc length of a curve C given an explicit defined function y equals h of x over the interval x of 1 to x of 2, and we were using this formula. As I was telling you, that one is for explicitly defined functions, right? When we have y equals f of x, h of x, or something like that. Okay, today what we're going to do is we're going to redefine this, and you're going to learn how to find the arc length for a parametric equation. You're going to see that these two formulas are very closely connected, okay, and I'm going to show you the connection. Okay, so as usual, we have C is represented by parametric equations, and your x is going to be f of t, and your y is going to be g of t. You have an interval, okay, the t is bounded by a and b. Then what you have, okay, following the formula that we learned, okay, at the beginning of the year, we have this. Don't let the dy dx to intimidate you. You know that that's the Leibniz notation. Okay, so we start with this. This is what you know, what you love, what you have used. Okay, now you know that dy dt, okay, by the formula that we just learned from the previous page, is dy dt over dx dt. Okay, this is the dy dx. Okay, so we know this from the from the previous page. Okay, now what you know is by properties of exponents, and because you know fractions, we can split this as this. Do you agree with that? So what you're doing is you are just splitting the parentheses. Okay, after that you're like, okay, I want to have both of them common denominator. So this guy, what you're going to do with this one, this is going to be a dx dt over dx dt, all of it square, so you share the same denominator. You are not doing anything magical here. You are just doing some algebra 2 here. So you have the situation. After that, you are going to again use properties of exponents. Okay, using dividing the radical. Okay, not dividing the radical, but splitting the radical into the numerator and the denominator. Why? Because when you take out the denominator, okay, forget about this. Think that you have this equation like this. Okay, you know that the square root of dx dt square is going to be dx dt. Okay, and then here is where tricks get a little bit, let's say, dirty. Okay, since I have this dx, I'm just going to put dt dt because they cancel each other. So I just strategically, what I'm going to do here, I cancel this with this. Okay, and then you have this beautiful thing that it's exactly the formula of the arc length of a parametric function. Okay, so parametrically defined function. Isn't that beautiful? Please note that the formula works when the curve does not intersect itself on the interval AB. Okay, and the curve must be smooth. What is being smooth? That it's differentiable. Okay, that it's differentiable. If it's not differentiable, you cannot take the antiderivative. Okay, because that's what the integral is the antiderivative. Okay, anyway, okay, so what we're going to do here is we're going to set up the integral expression for the arc length of the curve given by the parametric equations, and they give you x is equal to e to the power of 5t plus 2, and y is equal to 3 times sine of t squared. Okay, and the t is bounded by 0 and 4. They tell you not to evaluate. So what are we going to do here? Well, the first thing that I'm going to do is I'm going to find dx dt. Okay, you know that dx dt is going to be e to the 5t plus 2 times the derivative of the numerator, not the numerator, of the exponent, right? So which is 5. Okay, so this is going to be equal to 5e to the 5t plus 2. Okay, similarly, we're going to find the derivative of the y, okay, part. Okay, what's going to be this derivative? Well, you know that this is going to be 3, the derivative of sine is going to be, sorry about that, it's going to be cosine, right? Okay, so you know that it's cosine of t squared times, okay, the chain rule, okay, the derivative of the inside 2t. Okay, so you know that this is going to be equal to 6t, okay, cosine of t squared. Okay, now that we have both derivatives, we just replace it in the formula. Okay, so what you have is thus, we have that s is going to be equal to the integral from 0 to 4, where 0 and 4 comes from the hypothesis of the problem. Do you see it? So pretty nice. Okay, so square root of dx dt, which is going to be what? 5e to the 5t plus 2 square. Don't forget about those squares. Plus, and then 6t cosine of t square square. Okay, all of this should be inside the square root. Okay, all of it, and don't forget your dt here. Okay, and that's the setup. Now you're going to tell me, well, that integral is absolutely horrendous. Yes, that's why they are telling you not to evaluate. If you want to evaluate that, I highly recommend you to use a CAS calculator. Okay, so that's it for today. I hope that you find this video helpful. Bye.